Hi, this video will continue discussion on the deformation from axial loading. Last time we come up with this formula, the change, the deformation is summation of each segment, and we have PL over AE. And be aware this P is the internal force for each section, and that number will be different for each one. And L is that particular length in that section. A is area for that section, and E is elastic modulus. And one thing I want to add on today is about sign convention. Because sometimes that section, one section could be in elongation. So if the section is elongation or it's in tension, internal forces, then we know this delta, the deformation should be in positive, right? And if it's contraction, and cause shortening by compression, in that situation, that section gonna consider deformation in negative, and then you can sum them all up. Okay, so now let's look at this example. You have these four forces, and let's first look at it. Is this at equilibrium? And this showed, and let's take a look. There's a 5 kilonewton going to the left and a 7, so 5 plus 7, that's going to the left. And going to the right, we have 8 plus 4, so that is indeed correct. They both are 12, and this showed, like we said. Now we're going to look at sections. How many sections do you see for this one? All right, so you see 3, right? So then let's take first look at this first section, which will be right here, this area. So if you are looking at this section, so arbitrarily, if you cut anywhere random during this yellow highlight, for example, if I cut over here and I continue that right here, I have left side and right side. And if we are looking at FBD on the left section, that'll be easiest. And what do we have? External force, we have this 5 kilonewton. And now we want to find out what's the internal force, what this P is. And internal force, if I were to use a different color, is in red. So that will be going this direction, right? That's going to be our internal force. And that's 5 kilonewton. To balance this external force, 5 kilonewton. And be aware, look at this 5 kilonewton. It's in tension, right? So that will be positive for that elongation. All right, now let's think about deformation in that particular AB section. So we're looking at AB. So this is in AB section. And so the elongation, delta 1, delta AB, that will be equal to P. This internal force is 5 kilonewton. And now we needed to know the length for the LAB. So if LAB here is said it's going to be 2 meters long, okay? So it's going to be times 2 meters and divide by area. So we assume this is uniform bar. So the area, let's make it to be, let's see, let's make a 0.5 meters square. Okay, so that's going to be the cross-section area. So we'll have 0.5 meters square for this cross-section circular area. And our E, we assume this is a 36 steel, and our elastic modulus will be 200 gigapascal. Then that will be our E, so 200 gigapascal. All right, now let's think about the unit. So let's first look at this one. Pascal and times area, so gigapascal times meter square, that will give us in what? Giga force, because Pascal is Newton per meter square. So that's going to give in giga force. And then how about if we change this 200 gigapascal, giga to kilo, right? Because you have kilo right here. So 1 giga is going to be 10 to the power 9, and 1 kilo is 10 to the power 3. So in other words, 1 giga is going to be equal to 10 to the power of 6 kilo. So knowing that, we're going to change this right here. We're going to times 10 to the power of 6. So we're going to change gigapascal to kilopascal. So knowing that, we will have gigapascal cancel out. Then we'll have kilopascal, and kilopascal times meter squared, that will give us in kilonewton. Alright, so let me continue to write. So that will be 10 kilonewton meter, and this will be 0.5 times 200 times 10 to the power of 6, and that's going to give us in kilonewton, and that cancel out. Then you will get a unit of in meter. Very small number, right? Okay, so you can leave it alone and we can calculate at the end, but I'm just going to calculate at the end once we figure out the units now. So now let's look at our second section. We figure out the AB now. That's how much deformation happens in AB, and AB is subject to tension, 5 kilonewton. Now let's look at another section. Let's look at this midsection where BC is. So during the, so for BC section, if we were randomly to cut anywhere, if we were cut somewhere here, and we were extending that, so you have left and right. Again, I'm going to choose left. I think a right one will work as well. And then let's put all the external forces, like how we did in internal loading, right? Back at the beginning, you have 5 kilonewton here, and now we're going to include this B, because this B, this 8 kilonewton is applied at point B, so we do need to consider that one. And then where the dashed line is, that's where the internal force is, and I'm going to use red color. Now let's think about it. So 8 kilonewton to the right, 5 to, so this one have to be going to the left, will be 3 kilonewton. So 3 plus 5 will be left for 8 and right for 8. And now let's look at this one. So this section will be certainly be compressed because this 3 kilonewton is pushing it in. So this earlier, this is in tension. This is going to be in compression. If it's in compression, be aware this section, this BC section is going to be compacted. It's going to be having a negative deformation because it's contracted. So knowing that, we're going to write down the expression for our BC section. I don't know what just happened, but let's see. So the delta BC is going to be using PL over AE, our formula. And be aware, their P here is different. It's going to be -3 due to compression. And L, so the length BC here, they tell us it's 3 meter. And by the way, I'm going to put the CD 4 meter. So that's going to be 3 meter kilonewton and 3 meter. Okay, so then the area, it's the same, and it's 200 gigapascal. Okay, now you can do the unit conversion, but here I'm going to leave alone. And then the last section, which is our section CD. So at last section, section CD here, we're going to understand, first of all, what's the internal force will be. So if we randomly cut anywhere, if we cut over, I erased the whole thing. If I cut over right here, and then I'm going to draw my FBD, and obviously it will be easier to look at the right section, right? So we'll put all the forces that's on the right section. We have the 7 kilonewton pushing to the left. And then, do we have any other external forces? The answer is no, but you might argue, you said there's a 4 kilonewton right here going to passing. But understand, even this arrow going to where you cut, but where is this force applied at? Is at C. That's not where we cut, right? So 7 kilonewton is the only external force down there. And then knowing that, we're going to figure out what's going to be the internal force on this last section CD and have to be balancing going to the right direction. So that would be 7 kilonewton. And now if you think about it, this section, and since this at where we cut is going to this direction, that's a compression. It's compressive. So that's a compression. Again, in this section, our delta, our deformation, should be a negative value. So now we write down delta CD is going to be equal to PL over AE. And our P, this internal force, is negative 7. And our length we defined earlier as 4, right? 7 kilonewton times 4 meter. And area is 0.5 meter square. And E is 200 gigapascal. So far, you have looked at each individual section. Now, they want to ask you, look at this entire ball holistically. What's going to be the deformation? So we're going to add this whole thing together, PL over AE, right? So if you pay attention, you realize A and E, it's the same for each 3 sections. They have the same area, they have the same material. So in that situation, I could put them all together like that. 0.5 meters squared times 200 gigapascal. And that's our A and E. And since we did a unit discussion earlier, we know if we want to change this gigapascal to kilopascal, we're going to times 10 to the power of 6 here. Okay. Now, the numerator is basically each of the 3 sections, their PL product. The first one is 5 times 2. It's positive. The second one, BC section, is negative 3 times 3. And for our CD section is right here, negative 7 times 4. So that's our summation of the PL. And be aware the units for this will be force is kilonewton and L the length is in meter. And if we look at the units one more time, and the bottom one is going to give us in kilonewton, right? Kilopascal and a meter square going to give us in kilonewton. And then they cancel out that. So everything add up together will give us the unit of meter, which is deformation, how much change in the length happens. So now let's just put into our calculator. So I have 10 minus 9, then minus 28, right? So I will have negative 19 on the top. So negative 19, then divided by everything at the bottom. Let's put the bottom together. So that's 200 times 0.5, that gives 100. So it's basically 10 to the power of the 8 on all of them. Okay. And let me see. 10 minus 9 minus 28. 1 minus. So I get negative 27 on the top. Okay, so in that situation will be negative 27 times 10 to the negative 8. That's how many meter. And to make this a little bit better looking, will be negative 2.7 times 10 to the power of 7 meter. Still, it's kind of hard to comprehend, right? So let's make that to be a micrometer or nanometer. So we micrometer, maybe change to nanometer, because we know 1 meter is going to be 10 to the power of 9 nanometer. And so in that situation, we're going to get negative 270 nanometer change. Negative means this entire bar is going to shrink a little bit. And shrink how much? 270 nanometer. It's very insignificant. You know, we cannot see it, but it does happen. The contraction does happen. Imagine if this external force has changed dramatically, has increased. Yeah, in that situation, we can see some more drastic deformation. All right, so this is example for axial loading the deformation. Now also you see where incorporate the sign convention into it. All right, I'll see you at the next one. Bye now.